AI predicted the failure correctly. It identified the right component, the right failure mode, and a predicted failure window of 18 to 24 hours with 94% confidence. The maintenance teams were notified. A response window was scheduled. Everything was proceeding as designed. Daniel looked at the predicted window and knew it was 6 hours too late. Not wrong about what would fail, wrong about when. The component failed at hour 12. The maintenance team arrived at hour 18. 6 hours of difference, one unplanned outage. The AI predicted the right failure at the wrong time, and understanding why and what Daniel knew that the AI didn't is what we're going to talk about today. AI-driven predictive maintenance is now standard in enterprise network operations. Cisco Predictive Networks, Juniper's Mist AI, Avista's Ava. These platforms analyze component telemetry continuously, terminal readings, error rate, utilization patterns, and predict failure windows before the failure occurs. The goal: replace unplanned outages with scheduled maintenance. In most cases, the prediction is accurate enough to be useful. The AI identifies the right component. The maintenance team responds. The failure is caught in a planned window rather than an emergency. A 2025 IDC report on AI-driven network maintenance found that predictive AI reduced unplanned outages by 58% across enterprise environments, with 91% accuracy on component identification and 74% accuracy on failure window prediction within a 12-hour range. 74% accuracy on failure windows within 12 hours. That sounds reliable until you consider that the 6-hour error in a predictive failure window, which falls well within the AI's documented accuracy range, means the difference between a scheduled maintenance response and an emergency outage. Any conditions of accelerating degradation, where a component is failing faster than its historical failure curve. The AI's prediction is not just imprecise, it is systematically late. AI failure prediction uses Weibull distribution models, a mathematical framework specifically designed for failure rate analysis. The model takes real-time telemetry, terminal readings, error rate, utilization data, and plots the component's current position on a failure probability curve trained on historical failure data. When the probability crosses the model's alert thresholds, a failure window is predicted. This is genuinely powerful. The model can predict failure days before any human operator would notice the component was degrading. And it is right about what will fail the vast majority of the time. The limitation is in the timing, and the timing limitation is structural. Daniel's component was operating at sustained temperatures above its design specification, not dramatically, but consistently for 3 weeks. The Weibull model the AI was using did not account for sustained terminal stress as a failure acceleration factor. It predicted a component would fail when components of this type typically fail. Under terminal stress, this component was failing faster than typical. The model was right about what, it was wrong about when. The AI's predictive model correlates each telemetry stream independently. Terminal readings against terminal failure thresholds, error rates against error rate failure thresholds. It is extraordinarily good at identifying when any individual stream crosses its failure boundary. What it does not do is most deployments. It correlates the rate of change across multiple streams simultaneously as a failure acceleration signal. Daniel was doing that manually. He was looking at how fast the error rate was climbing and how fast the terminal reading was rising, and calculated from those slopes when the component would reach its failure thresholds, not when components of this type typically reach it. Daniel pulled the error rate data from the past 96 hours, when the AI's predictive model was seeing an error rate that was above baseline, but within the range associated with end-of-life behavior for this component type. Predictive failure in the 18 to 24-hour window. What Daniel was seeing, an error rate that had been increasingly linear for the first 72 hours, consistent with the AI's model, and had been increasingly exponentially for the last 24 hours. The slope had changed. The failure curve had steepened. It plotted the acceleration phase separately, extrapolated the exponential slope to the component known's failure threshold. The intersection was at hour 12, not 18 to 24, 12, 6 hours before the start of the AI's predicted failure window. He spent 4 hours making the case. The operations team's response was reasonable. The AI's model had been trained on thousands of component failures. Daniel's recalculation was based on 96 hours of data and a slope extrapolation that assumed the acceleration would continue. What if the error rate plateaued? What if the terminal stress was being managed by the cooling system? Daniel's counter, the cooling system terminal log showed no change in airflow. The error rate had not been plateaued in 24 hours of exponential growth. The probability that it would plateau now, when the slope was at its steepest, was lower than the probability that the AI's model was using the wrong reference curve. The maintenance team was dispatched at hour 9. They arrived at hour 10. The component failed at hour 12. The failure was caught in a controlled response. The component was replaced in a 40-minute window. Zone 2 remained online. If Daniel's escalation had not been accepted, if the team had responded to the AI's predicted window, then they would have arrived at hour 18. Zone 2 would have been offline for 6 hours. The AI predicted the right failure. Daniel predicted the right time. Both were necessary. Neither alone was sufficient. Daniel's value in this situation was not that he caught an error the AI made. The AI was not wrong. His failure prediction was within his documented accuracy range. A 6-hour prediction error on a 12-hour failure window is a 74th percentile outcome, well within the AI's known performance envelope. His value was that it could read the failure acceleration signal, the inflection point where linear error rates become exponential, and recalculate the failure window using the actual slope rather than the population level. The framework Daniel was applying is not proprietary. It is taught in network reliability engineering and documented in hardware reliability literature. But most organizations deploying AI's predictive maintenance have not built it into their standard operation procedures because the AI prediction has made it feel unnecessary. First, watch the error rate slope, not just the error rate. A linearly increasing error rate is consistent with normal end-of-life degradation. An exponentially increasing error rate, where the slope itself is steepening, is a failure acceleration signal. Second, correlate the error rate slope with the terminal gradient. Terminal stress accelerates the failure curve. If both the error rate and the temperature are increasing simultaneously, the failure window is compressed relative to the MTBF baseline. Third, identify the inflection point, the moment where the error rate transitions from linear to exponential growth. Extrapolate from that inflection point, not from the beginning of the degradation period. The AI's model often uses the full degradation period, which dilutes the acceleration signal. 6 hours is not a small error when the consequence is an unplanned outage. The engineers who matter most are the ones who understand that AI failure prediction gives you the right component and a useful probability distribution, and who know when to recalculate the timing themselves. That recalculation requires understanding how failure curves accelerate under stress. It requires knowing when the AI's model loses resolution, and it requires the confidence to present a manual calculation against a 94% confidence AI prediction and hold the position until the data supports it. The AI failure prediction system of 2030 will be substantially more accurate on failure window timing. Several vendors are already building failure acceleration correlation into their predictive models, correlating error rate slope changes with terminal gradient in real time, rather than comparing individual streams against static thresholds. Cisco's most recent predictive network update includes an experimental degradation velocity metric that is precisely the multi-stream acceleration correlation Daniel was doing manually. This is how good tools get built. An engineer identifies a gap between what the AI produces and what the operational decision requires. They develop a manual methodology to close that gap. Eventually, that methodology gets formalized into the model. A 2026 Gartner Infrastructure Prediction Report forecasts that AI failure window accuracy will improve from the current 74% to above 88% accuracy within 12-hour ranges by 2028, driven primarily by multi-stream acceleration correlation models replacing single-stream MTBF baselines. The roles being created right now are not the ones that watch AI predictions, they are the ones that validate them. Failure acceleration analyst, engineers who maintain the manual recalculation methodology as a check on AI prediction timing. Predictive model validators, who systematically compare AI failure window prediction against actual failure times and feed the gap data back into model retraining. Infrastructure reliability engineers, who understand the phases of hardware failure well enough to know when the AI's population level model is using the wrong reference for a specific component in specific conditions. These roles are being created right now in the organization that know the AI is right about what will fail and know they need a human to tell them when. Zone 2 ran without interruption. The component was replaced in a 40-minute controlled maintenance window. Daniel filed the failure acceleration analysis in the incident report, the first time that specific methodology had been formally documented in the organization's post-incident records. The AI predictive model was submitted for retraining with the accelerated failure data from this incident included. Daniel's recalculation will be in the next version of the model. Until then, and until the model after that, and the one after that, someone needs to be in the room who knows how to read the slope when the curve is accelerating. The AI predicted the right failure. It predicted the wrong time. The engineer knew the difference because he could read the slope. If Daniel's story gave you something, drop a comment. Has a prediction system ever given you the right answer at the wrong time? What did you know about the timing that the model didn't? Because that knowledge is exactly what gets built into the next version of the model, and most of it all still sitting undocumented in the heads of the engineers who generated it. Next week, an AI abnormality detection system that flagged 200 alerts in a 12-hour window. One of them was the precursor to a cascading failure that would have taken the entire data center offline. The engineer who found it, not by analyzing the highest confidence alert, but by looking at the lowest confidence ones, and what that tells us about how AI abnormality detection and human pattern recognition work together. Subscribe so you are there, and if this gave you something to think about, Share it with the engineer who has been doing failure acceleration analysis manually and calling it instinct. That instinct has a name now.